And he was showing that there's like this is a bump.
By setting it to a temp.
But that bump is not in the.
Okay. But it's suggested just by doing that.
Yeah. Yeah, I was curious about that too.
It uses system models, but there's also the.
And I think
This.
observations
That's
that
suspicious.
happen.
So it's wrong.
But when he stitches it together,
That's-
it's
that
like.
sounds good. I'm just, you know.
You want to switch it up?
Sure, unless you, I think I got acquainted with this thing.
Yeah.
Yeah, so apparently you just put the 15, right? You get the-
Everybody.
Right.
And then beeps and then stops.
Right.
So you're missing something.
And just monitor if you want stuff.
Yes, yeah, so just here, this window, every now and then, so I know you've done this before, you can see messages from Kevin, so Kevin is our IT director. And so he might tell you, like, we're struggling, he might say, oh, you can do this, or you can do that. If you want to message Kevin, like, you can see here, if you send something, it's for everyone.
Yeah.
If you want to reply something to Kevin, you have to choose
Mhm.
that.
Okay.
Yeah.
And if people are unmuted, you can.
And can mute them,
Yeah, right.
It's just, yeah. It's
Well,
easier to do.
participate.
Yeah, that's very, yeah, okay.
You know, to be skip by.
Do what?
There's a lot of those.
Yeah.
Cool stuff. Cool stuff. And bugs.
Only females would have to email. He's doing that.
We're doing this, yeah.
I need more coffee.
Copy here.
Actually,
Check to the head.
that would be really good. Bloody Mary.
No.
Yes, okay.
This.
Yeah, the direct measure. These,
Yeah.
There was people leaving me.
They have. Oh, I used to be.
Okay, thank you, everyone. I think we're caffeinated, we're fed, and so we're ready for the next session. And we want to be on time, so we're starting at 10 before. So the first speaker is going to be Rachel Plesha, and is going to tell us about some 2% accuracy for HST with COS and STIS.
Awesome, thank you. Everybody hear me? Perfect. So yeah, I'm Rachel Plesha. I work here at Space Telescope. And in the past couple of years, I've been working with Gisela De Rosa on reaching 2% local flux precision with HST and COS and STIS to enable EGN reverberation mapping, which might be the longest title. So I'm going to talk a little bit about the calibration work that we've done in order to enable this. So starting first with a little bit of background about the program. So we observed the AGN Markarian 817 with COS approximately every other day from November 2020 through February 2022, for a total of 165 epochs. Over the same time period, we observed Markarian 817, also with STIS, about every 4 months for a total of 6 epochs total. We finally observed the standard star WD0308 565 with COS about once a month for a total of 12 epochs total. This is in addition to the standard monitoring that the COS team does of this white dwarf about every 3 months. So the AGN Storm project observes from the X-rays into the infrared. My focus really was on the HST portion, so in the UV into the near infrared with STIS. With COS, we observed with 3 different central wavelength settings, G130M 1222, and G160M 1533 and 1577. This gave us full coverage in the FUV, excluding Lyman alpha airglow on the detector. With STIS, we always observed with the NUV MAMA G230L and the 2 CCD settings G430L and G750L. For the later half of the observations, we also have 140L observations, which gives us some overlap with COS. So you can see the spectra here. And yeah, that's it. So the calibration requirements for COS and STIS are both a global absolute flux accuracy of about 5%. For COS, the 1222 FUVB setting is a little bit higher due to the lower throughput there. They both also have a global relative flux accuracy of about 2%. For the AGN Storm project, we are looking for, in order to enable the velocity resolved reverberation mapping, we need stable and repeatable measurements. And what this translates to us as is a local relative flux precision of 1.5 to 2% when compared with the same white dwarf model across both COS and STIS. And so we're looking, that's why we're observing WDO 308, and so that we're looking just at a single white dwarf rather than using multiple white dwarfs across the calibrations. So talking a little bit more about what we did for the COS calibration work, we really focused on updates to the sensitivity functions. We decided that we were going to just use exclusively the data that we observed of WDO 308 rather than adding in any of the COS monitoring observations. Several reasons for this. Main reason is that we had higher signal to noise than those of the COS observations because we were only taking the data for 3 central wavelengths rather than all of the central wavelengths that are being monitored by the COS team. We ended up making 12 different response functions for each of those epochs. And we also needed to add in an additional breakpoint to the time-dependent sensitivity function that's used in the standard pipeline. So I just want to note that we are trying to use the COS calibration pipeline and the STIS calibration pipeline and just improve upon those rather than starting the calibration from scratch. The COS team, this COS calibration work was done in 2022, and since then the COS team has delivered a new time-dependent sensitivity function as well that has an additional breakpoint. So it's great to hear that we agree on that. So just showing some of the response functions to show you that we're not doing anything too crazy. In black are the data points for one of the epochs of WDO 308, showing the net counts divided by the CalSpec model. And on the bottom are just the residuals of how good that fit. Oh, sorry, and in red is the spline fit that we've done, excluding any bad pixels and absorption lines. So masking those out, we're not fitting those. And so the residuals on the bottom just show how well we're doing of that fit. And so we were pretty happy with those. And so the real test was then to see how we are doing when we actually calibrate the data. So on the top here is the residuals of the data when compared to the CalSpec model. And on top is with the default pipeline. And you can see that the COS team is doing within the 5% global accuracy that is in their requirement. But there's still a lot of structure as well as some time dependence that you can see if you stare at these a lot like me. So on the bottom then is if we, with each of our response functions, if we then calibrate the same data, we're seeing a much flatter residuals here. And so we're getting within our 1.5% local accuracy that we're wanting with the COS calibration. So showing this in a little bit different way, kind of the same information. Here, each of the lighter circles represents the default calibration with COS, and each of the darker circles represents the Storm 2 calibration pipeline, if we'll call it that, the new reference files that we have. And so each panel here is a different epoch that we've done. So each of these is calibrated with its own response function. And I've highlighted a couple of cases here just to kind of show the extremes of how well we're calibrating, especially the time dependence out with that new breakpoint, as well as the structure. So moving on to the STIS calibration work that we did. So for the STIS calibration, similarly to the COS calibration, we created updated sensitivity functions for the two MAMA settings, G140L and G230L. We used STIS data of WDO308 from an HST special calibration program that was aimed at standardizing the fluxes between COS and STIS. Information about that's in the corner. You should check it out if you're interested. It's a cool program. We also found that we needed to update the time-dependent sensitivity function for G140L. For G230L, we were happy with it. I was a little concerned after Daniel's talk, but I think we're still okay because of when our data was observed. Something that surprised us that I'll talk a little bit more about is that we need to update the extraction box sizes for G140L and G230L. And finally, for the CCD settings, we really didn't do too much, except that we used the STSCI provided tool to apply the diffringing to G750L. So if we look at the residuals for STIS calibrated with the default pipeline, you can see that it's well within the 5% global accuracy and pretty close to the 2% global accuracy, relative accuracy. I don't know. Too many relative global. I confuse myself all the time. But there is still a little bit of structure still in the residuals that we wanted to try and correct out. And so if we create new response functions similarly to how we did with COS, we can see that we're getting a much flatter residuals here with the Storm 2 pipeline at the 2% local accuracy level. So talking a little bit about the extraction box size, we were very surprised by this, but when we started looking at the time-dependent sensitivity data, we were seeing residuals that didn't quite make sense to us. So we went back and took a look at the 2D 2D spectra of the data, and looking at the extraction box size with the default extraction box size of 11, shown in pink here, we were seeing that although the documentation said that the default should be enclosing about 85% of the flux, when we calculated it, we were getting closer to 70 to 73% of the flux. If we expanded that to an extraction box size of 21 instead, which is another supported mode, or supported size for the extraction box size with the default calibration pipeline, we're instead getting much closer to that 85% in around 83%, 81 to 83%. So showing just the residuals I was talking about, if we just look at the only changing the extraction box size, so not even talking about any of the updates we did to the FLUX calibration or the time-dependent sensitivity, we can see that the extraction box size of 11, the default, has a lot of scatter here. But if we increase that to 21, we're getting much less scatter here. And so that surprised us, but it really did explain what we were seeing. And the scatter that's left, we found is due to the time-dependent sensitivity, which we then updated. So here, again, the darker circles are the updated calibration and the lighter circles are the default calibration. And you can see, especially in 2024, the lighter circles are much higher from 0 from the model. And so we don't have data in 2024, so we don't really care about that. That's good to know. But even in 2020 through 2022, the lighter circles appear to have a slight bias towards the top. So adding a new breakpoint really did fix that for us. Okay, so just, how does this look? Okay, I was worried about this plot on this like tiny TV, and I'm glad the projector is here. So this is just kind of a summary of the residuals for G140L and G230L. Again, lighter circles, default calibration, and the darker circles are our calibration. And you can see that we really are correcting out some of that structure we were worried about. G230L in particular already was doing really good job. We didn't think that we need to do too much there, but there was a little bit of structure still, you can see kind of in the middle here, that we wanted to correct out. And so we felt pretty happy with these results. And so we moved on to the CCD settings. And for those, we really didn't touch anything in the end. But for G750L, we used the diffringing tools. Yeah, so for both of these, we're within the 2%. There still is some structure, as you can tell. But when we tried to improve this, like we did with the other modes, we really were making things worse. So we decided to just move forward with this because even though it's not perfect, it's doing a really good job overall. So moving on to a few lessons that we learned that hopefully we can pass on to you. So first, that reaching a 2% local flux precision is very possible with HST costs and STIS for those who need it. However, it was really difficult to reproduce the HST calibrations. We had many help desk questions that we sent in, and we're very grateful for the answers that we got and all the help that we had with that. Widely sharing the code and the process that goes into making these reference files would be extremely helpful in allowing others to recreate these calibrations and then improve upon them. Along those same lines, keeping an open line of communication between like the research and the instrument teams at STSCI for HST and JWC and Roman, of course, is really essential as well. Like, so if we find something, we can then go and communicate that to STSCI so they can go and look into it some more and decide if that is something that is actually wrong or if we're just crazy. And vice versa, if you are working, or if they're working on something, it's good to know so you don't then repeat the same work. I think that this conference is a great step towards that. And then a little bit more specifics, something I didn't talk too much about because there's 15 minutes, is that there may be a time dependence in the cost flux calibration that's independent of the TDS correction. We saw this on a scale of about 3 months, which is why we ended up delivering 12 different response functions rather than just a single response function. That was something interesting that we saw, but we didn't look into further because we didn't need to. And then just finally that the default STIS extraction box sizes for point sources is too small, it appears to be. And it's affecting the flux calibration. And so that's something to think about, maybe. And then finally, just putting up here our papers about AG and Storm. If you want to go learn more about what we've actually done with this data. Our paper number 2 talks a little bit more about the cost calibration that we've done. And we're working on the STIS data paper as well. We have high-level science products that include the data that we observed, as well as the reference files. So if you're interested in that, go check it out. We hope to have the STIS data products added there soon. And so with that, take any questions.
Any questions for Rachel? John, you can just speak up. Thank you.
Okay, John Debus, Space Telescope. So remind me when those STIS extraction box observations, what time period did they cover?
So those are the time-dependent sensitivity observations. So they cover all time.
Okay. Did you see the majority of the discrepancy with the smaller box size around, like, because there was a period of time when STIS was a little out of focus because they were not doing the focus correction quite right on the whole telescope. And so STIS was a little out of focus around, I think, 2015 to 2017. So to my mind, that would be when I would expect you to see the largest discrepancies with this smaller box size. Because the slightly out of focus would have spread the PSF just enough to maybe account for that discrepancy.
Yeah, that's interesting. I do not remember off the top of my head. I feel like I remember there not being a pattern. And I feel like I do remember there were some in like 2012. We did start looking only at post SM4, I should say. But yeah, I'd have to go look back. That's an interesting thought. I'll go back and look.
There's an ISR on the STIS focus history that would probably be what you would want to correlate to if it was there. The only other thing I could think of is breathing, right? Yeah. But that would be on more of an orbit to orbit time scale.
I mean, 21 is like very large, no? That's a little.
That's a big extraction size. I hope you'd catch all the PSF there.
It's the biggest before you go to an infinite aperture. Yeah, we did look some at the focus, like the telemetry, to see if we could correlate anything, and we didn't see anything. But I'll have to look back at that and see. It'd be interesting.
Any other questions online? Quiet.
I've convinced everybody.
Daniel, yeah.
This is a little biased for my own purposes, but I wanted to ask, for the TDS reference file you created, what was the breakpoint that you used?
Yeah, we actually had I looked this up after your talk because I like freaked out. So we actually had 2 breakpoints, one in 2015 and one in 2022.
Okay. Interesting.
Yeah.
Any final questions? Okay, let's thank Rachel again, and we'll. Okay, we'll move on to the next speaker, telling us about UVEX calibration, Hannah Earnshaw. Take it away. Thank you.
Thank you very much. Yeah, my name is Hannah Earnshaw. My pronouns are they, them. I am a staff scientist in the high energy astrophysics group at Caltech, and I'll be talking to you today about the calibration requirements of the Ultraviolet Explorers. This is NASA's latest selected medium explorer mission. We're currently in phase B, and I'm giving this talk kind of on behalf of the science team. Our PI is Fiona Harrison. Some of our science leadership here on this screen. So if you know any of these people, please ask them about the science we can do with UVEX. I'm up there in the corner. I'm the science team coordinator, which basically translates to I know a little bit about a lot of things, not a lot about everything, but hopefully enough to give this talk. So, to start off, I'll give you just an overview of our science goals, what we actually want to achieve with UVEX. We want to look at the low mass, low metallicity galaxy frontier. So we'll be surveying the sky to find these local analogs to the sort of high redshift galaxies that JWST is seeing, which we expect to really pop out in the UV amongst all of these very optically faint galaxies. We want to follow up some of like the best kind of local analogs with UV spectroscopy to diagnose a nebular emission. And then we also want to do a dedicated survey of the macrogenic clouds to basically use this local low metallicity laboratory where we can resolve the stellar population. We can do spectroscopy of individual hot and strip stars in particular, which we have just not had an opportunity to do much of at all up until now. We also want to be responsive to the dynamic universe. So lots of cosmic explosions are UV bright in the first few hours. So we really want to get onto these things fast. We want to probe the UV emission from merging neutron stars or neutron star black hole mergers potentially. So tiling the error regions of gravitational wave detectors. We want to perform spectral follow-up of the first hours of core collapse supernovae, looking at this shock breakout emission lines that quickly disappear again after 12 or so hours. But we also want to use a significant fraction of our prime mission observing time for community TOOs, so targets of opportunity follow-up, based on the priorities of the astrophysics community. What interesting transients and variable sources do they want to look at? So we'll be kind of figuring out exactly how we do that over the next little while. And then finally, we just want to leave a useful legacy of state-of-the-art UV data. We'll be surveying the whole sky in the UV, NUV, and FUV bands for the first time down to a depth like kind of similar to state-of-the-art optical and infrared surveys. And hopefully open up a vast discovery space so we can study things we haven't even thought about yet. So how are we going to do this? So UVEX kind of has 2 main parts. We've got this over 12 square degree field of view imager in NUV and FUV bands, which are mostly matched to Galax. So the FUV is about at 1600 angstroms, NUV around about 2300 angstroms. With a PSF just around about 2 arc seconds. So that's also a major improvement upon Galax as well. And that's sufficient to resolve all but probably like the densest regions in places like the Magellanic Clouds. but we'll be able to cope with pretty much everything outside that. And then we also have this very long slit spectrograph, 2 degrees in length, mostly 2 arcseconds in width, but we're kind of playing around with having multiple options there, from 1150 to 2650 angstroms, are greater than 1,000 across this whole band. And the thing is, like, both the imager and the spectrograph will be constantly running and constantly taking data. So even if we're doing imaging surveys, the spectrograph is just going to be chugging away, getting serendipitous stuff. And then if we're looking at spectroscopic target, the image is just going to be, again, plugging away, picking up whatever random transient happens to be going off in the area at the time. So we'll be building up all of this serendipitous data as well. So these capabilities come with a number of calibration challenges. So we have our wide field of view. We're using 3x3 arrays of 4K CMOS detectors. Between the FUV and OUV planes and the spectrograph, we're dealing with over 300 megapixels of pixels to worry about. And we want to be able to be well calibrated across the entire field of view. We'll be looking at sort of big crowded fields. We'll have transients at unknown positions at unknown times. So we want to understand all that. We'll be performing a cadenced all-sky survey. So we'll be visiting every part of the sky, hopefully around about an average of 10 times over the course of our 2-year prime mission. And we'll be coming back to fields at different times of year, at different roll angles, because our roll angle is dependent on the position of the sun. So we'll need to be able to kind of deal with that when it comes to stacking our images to kind of build up our photometric catalog and perform difference imaging of fields against that are sort of arbitrarily rotated in relation to a reference image. So that's something to think about. We want to be comparable and compatible with other multi-wavelength facilities. So Rubin, Euclid. Actually, we kind of use some of the Rubin minimum requirements as a starting point to develop some of our own, just because we do want to be, pretty compatible with the state of the art elsewhere. And then there are some challenges as well that are kind of specific to the ultraviolet, and particularly the far ultraviolet, become more sensitive to contamination. So there'll be kind of calibration changes over time to think about in relation to instrument degradation and all that. And also in the UV is where extinction laws start getting steeper and start getting lumps and bumps in them depending on where you're looking. And so that's also something that we need to consider. So what I'm going to do now is I'm going to do a very quick whistle-stop tour of kind of where we're at in terms of the calibration requirements we're looking at. We're still early phase B. We haven't had SRR yet. None of this is set in stone, but just to kind of give you an idea of where we are at the moment. So in terms of photometric requirements, so we want our photometric systems to transform to a physical scale with systematic error of less than 20 millimeg, just under 2%. You know how requirements work. If you know all the sort of wording you have to do. But we have to, we want to be, again, kind of very compatible with Rubin. One of the drivers for this is creating UV to optical kind of SEDs to get good photometric redshifts for these low mass, low metallicity galaxies, where UV in particular is going to sort of break any kind of degeneracies caused by like the Lyman-Balmer break confusion and kind of just create the extra lever arm there. We want good repeatability. So we have requirement of less than 8 millimegs because we want to be able to get good photometric catalog measurements by stacking multiple visits. We also want to get reliable variability measurements. We want to minimize the amount of false positives we get and meet this all kind of across our field of view. We also want to know our color 0 points well. This will be important for extinction and color temperature variations, particularly in things like EMGW follow-ups where the color is a big kind of distinguisher between models. Very quickly kind of looking at spectroscopy. So this is like a sensitivity requirement, but it's driven kind of by measuring features in stripped stars, which we expect to be kind of faint, but we still want to sort of measure these wind features. But for context, like this is sort of providing overlap with, and specifically wanted overlap with the blue end of IUE, because we want to be able to be kind of compatible and comparable with the existing kind of archive of UV spectroscopic data, and then like this will also apply to the HST instruments. And then we have some relative and absolute throughput knowledge requirements. The relative throughput in particular is very important for determining C2O line ratios that we're looking at in these low metallicity galaxies, because at the very lowest metallicities, this is where kind of theoretical models start to diverge in terms of their predicted C2O ratios. So we can start kind of distinguishing between these kinds of models with this spectroscopy. So as I mentioned earlier, we're currently already in phase B. We're still actively considering what we need to do when it comes to calibration. White dwarf standards will be important. We're a UV mission. We need the hot stars. So people who aren't fans of white dwarfs, sorry, we want more of them. I think this number's already out of date, actually. But you know, there are tens of white dwarfs available. We don't know exactly yet how many of them are particularly suited to UVEX's observing scheme, but it's likely that we'll want to add to that number anyway. We also want to leverage kind of the sheer number of white dwarfs available with Gaia in terms of kind of using that somehow for our sort of photometric calibration across our field of view. I'm going to skip over some of this because we're running out of time, but that's other stuff that we're thinking about. And we really want to kind of make use of the other missions around out there to help kind of prepare the way for our calibration challenges. So I think already we have UVEX science team members are working on HST proposals to kind of expand our sample of well-understood white dwarfs. Our LMC SMC observing program will benefit from HSD imaging of the densest crowded fields that will help for sort of deblending and source identification once we get to it. We want to really understand our extinction curves. And so we want to be able to take out dust extinction at similar precision to our flux precision so that our flux precision is useful. But also that's kind of a circular thing. We hope that the UVEX data will then be useful in better understanding dust extinction throughout the galactic plane and Magellanic clouds and interesting things like that. Finally, we are having regular calibration conversations with experts. We have a sort of Friday calibration club going on where we're inviting speakers in to talk to the UVEX team about calibration stuff. Not all of us come from a UV background. I'm actually one of the undercover X-ray astronomer imposters Kristen was mentioning earlier, so I'm learning a huge amount through UVEX and from this conference. So I know a couple of people in this room already have agreed to speak to us. Thank you very much. And if you are interested in coming and sharing your wisdom with the UVEX team, please talk to me. I would love to set you up with a meeting there. And this is the point where I'd usually ask if there are any questions, but also if you have like more of a comment than a question, now is your time. We're actively seeking input. So thank you very much.
Questions for Hannah, a lot of them. Okay, let's start here.
Hey, I have a comment for you.
Thank you.
You will observe the small Magellanic cloud as part of the normal wide survey. We do not cover the large Magellanic clouds, but later on into the mission, we will get something that we refer to as unallocated time, because we basically run out of area on the sky. And for these opportunities where we will probably put out proposals to do something, and covering the large Magellanic cloud, for example, is certainly something very, very interesting.
Great. There was another hand here. Was there another question? Is that a no? No question. Okay. John.
So this is a suggestion, maybe. So in the last few cycles with Hubble, there have been many SNAP programs that have been looking at nearby UV bright white dwarfs. So there's, I think, a huge treasure trove in the archive of UV spectra of white dwarfs that would probably be a good starting point for your global network. So I encourage you to look at that. I can talk to you offline about what those programs probably are.
Yeah, let me know. That sounds really useful. Thank you.
Great. Over there. Yeah.
Hi, I don't know if I missed it, but what type of detectors are you using? Can you observe bright objects? And
Yeah, so we're using silicon CMOS detectors. We can observe bright objects. We're not worried about like saturation kind of damaging anything. We're also using a sort of high dynamic range readout scheme, and so we hope to be able to, in our sort of general observing strategy, be able to observe up to like magnitudes of around about 8 or so.
8.
Yes.
Any other questions? Nothing online? Okay, I want to follow up on that. So I was very intrigued about, the hope of using this telescope for very quick follow-up on transients. You mentioned, within the first few hours of them being detected. So regarding the detector itself, so for COS and STIS, right? So we worry about bright object protection, and that requires, we need to make sure that the detectors are not going to get damaged. Is that a concern? Or is there a plan for that quick follow-up, or maybe that's...
No, that's not a concern. I mean, like it sort of, even like bright stellar magnitudes, all that would happen is that we would just saturate. We're not worried about detector safety for bright sources like that. Obviously, we're still avoiding the sun and the moon, but like kind of, yeah, just sources on the sky, that's fine.
Any other questions? Carl, you can speak up.
I'll just speak. Yeah, so I'm very interested in the dust extinction part, the measuring part of it. But I think maybe one of the things to say to you and everyone in the crowd, this is your comment part, sorry, is that definitely in the UV is where things become more variable for dust extinction. And using an average relationship or law, right, is probably going to break down more and more in the UV. And so going to more flexible extinction curves is probably the answer. This is something we're seeing on your top point, the fainter white dwarfs are needing a more flexible extinction model for the UV. So I think it has impacts both on our flux calibration as well as what we're going to learn.
That's good to know. Thanks.
Any final burning questions? Okay, let's thank Hannah again. And now we're going to hear about ALMA flux calibration from Roger Kuznitsov.
Rüdiger Kneißl, yes.
Very close. I got close. Thank you so much.
So yes, it's going to be a little bit different talk, bringing you to the longer wavelengths. But I thought it might be interesting to see where ALMA is in calibration, and also some of the approaches, the problems we are dealing with, and the approaches might be interesting to compare with. So yes, I'm going to introduce you to how calibration works, flux density calibration works for ALMA, and some of the recent changes, improvements we have made, and then how we evaluate accuracy and what the status is of that. So, but first I should say what ALMA is. So it's a radio interferometer at 5,000 meters in the north of Chile. And it's there because of the atmosphere, of course. It observes in receiver. Is this the right? No.
Are the arrows not working?
No, sorry. I'm just. No, it's fine. It's fine. So it observes in the from 8 to 0.3 millimeter. So it's yes. So the absorption is significant, and need to be at a high side, of course. And so we have actually 3 telescopes or arrays. There is a total power array that really scans the sky. It doesn't work as an interferometer. We have the 7-meter antennas in a sort of compact configuration for intermediate angular scales. And then the 12-meter array, you can see on the right here in this picture, basically gives us access to smaller scales. And with this transporter, we move the antennas out to 16-kilometer baselines, and then that gets us down to 5 milliarc seconds. So yes, then coming to the calibration. So the established way of calibrating in this wavelengths regime is basically through solar system objects. And we have started using them in most science data in the beginning. But of course, there are problems. They're not always available or suitable elevation. And they're not all of the same quality. I mean, they're from 3 to 5 up to 10%, depending on the object you're choosing, and also at what time you observe or frequency. So this is also a variable statement. And then the biggest problem is when we go to extended configurations. We have high resolution, and we basically resolve or even resolve out to some extent the sources. And if you remember, the interferometric response is even going to negative side lobe. So that is not ideal, and we have to choose point-like objects, and we basically transfer the flux with secondary flux calibrators and quasars that we choose over the sky. And I'll say more about this in a moment. Yes, I don't think I have I'm sorry, but I don't have the right slides here. This is not this is somehow the presentation got mixed up. So okay.
Did you upload to different versions?
Yes, I mean, I uploaded a new one and then the old one was deleted, but now I'm with the old one, it seems.
Oh.
So this is not.
We can try to.
Yeah. Can you?
But if it was deleted.
Like, so let's see what we have here.
Maybe it's still unboxed though.
Yeah, maybe it's still in the same directory.
So that was not the name of the file, I guess. 2024.
No, it's _2.
Okay, yeah, I go through. I improvise it. Okay, then I go straight to the. Then I go straight to explaining how we monitor the quasars. So we choose about 40 quasars over the sky in all LST, of course, and observe the 7-meter array because we need to include the solar system objects and monitor more frequently than 14 days. And they're also used for flux calibration, bandpass, and polarization calibrators, so we can choose from this set of objects. And we concentrate on 2 bands that are sort of in the middle here of the ALMA bands, which ranges here from 40 to 900. But we also extend with more occasional observations to the more distant bands to have a better coverage on the ACD. And the solar system objects, primarily we use Uranus as the main standard. But I'm going to say something in the next slide, in a slide that's coming later. So then this calibration data get reduced with the standard pipeline with some special heuristics and extra scripts, and then stored in a publicly available catalog. This can be accessed. And at the same time, we provide a flux estimation for for every source you can query this catalog, and you get a flux estimate with sort of ongoing improvements that we have made. And you can see here these points basically are daily estimates of the flux of that source at the reference frequency in each band is bands 3, 6, and 7 here. And for the higher bands and for band 1, we employ a curvature, so meaning we use a spectral index for the intermediate bands and a curvature for the outer bands, because the quasar fluxes are not just a spectral index, but they do show some curvatures. Okay, now let me explain to you the calibration method that ALMA is using. So actually, at this point, what I wanted to say, when we have the fluxes, we transfer them in the science data from the, and I don't have this now on the slide, but we have the flux calibrator and the bandpass calibrator in an observation. We have the phase calibrator, and we take measurements of the atmosphere and the loads, ambient and a hot load, and we use that to make a noise estimate, basically a calibration measurement, that then we transfer to the phase calibrator and to the target, which also has a calibration measurement. So that is done via the system temperature, and that's basically a noise term that's taken outside of the atmosphere on the source flux. So you have the instrument noise, you have the atmosphere contribution and the CMB, and that gives you, with capacity term, that gives you the TSYS. And it's measured with these loads. So you have the ambient and the hot load. And the way it's done is in order to minimize or remove some of the atmospheric model dependencies, the opacity term, we take the hot load and the ambient load to make a virtual load at the atmospheric temperature. And that basically makes the dependence on the model less and actually not critical for the flux calibration. Okay, and this is now a theoretical approach that we have used revisiting the ALMA goal of a flux calibration of 5%. And that basically takes all the technical requirements, but also measured assumed parameters. There's quite a number of them to basically connect those two things. And you can see here the different terms is the decoherence. So this is the interferometric decoherence, just like the seeing in the optical case. Then it's the Jansky-Poquelin, the conversion, which is the absolute normalization given by the solar system objects. In this case, you have the pointing focus terms, system noise, and then autocorrelation is basically the fluctuations in the atmospheric term and the bandpass. So that altogether gives 10 to 15% if you would use this absolute to calibrate through the system, which we're not doing. We're, of course, using a relative approach. So there are also numbers for the relative terms in this. And that basically depends, as you can here see for an example of the decoherence term, that depends on the atmospheric conditions and the frequency. So at high frequency, of course, you need good conditions that you get only 10% of the time. And so it depends, the accuracy depends basically on the conditions you're using here. And what's suggested to improve from this exercise is actually the planet models, doing the TSYS measurement more continuous. And as I said, sort of with the different calibrators, 10 minutes, 5 minute intervals, and addressing maybe the decorrelation in a different way. Okay, now I come to the solar system object. So it's basically Neptune, Uranus, and Mars, and primarily Uranus basically to have a standard that we're trying to sort of work with. And these are the ESA models that Herschel has been using as well. And here you can see the Planck, flux comparison is the CMB dipole. And yes, I wanted to explain this in more detail, unfortunately now. So we have done a comparison of our data with Planck, but we could not do the comparison at the time when Planck survey was done and the sources that were observed by Planck. So we had basically to bridge over with ACT. It's a CMB experiment from the ground-based, also in same side as ALMA. And basically the dipole, the flux, the CMB Doppler dipole from the Planck instrument is imprinted on the CMB map that ACT uses then to calibrate the sources of. And the agreement we find is 3%. So that validates the kind of approach we are choosing here. So what we have improved is the way we are doing the scheduling, and that's being done more efficiently now. We target the sources that really need to be updated, and we can so afford a faster, a higher cadence, and we can therefore afford adding the additional bands so that we can really cover the SED wider and then do this curvature fit and overall get a higher accuracy from this. So here's now showing you what this looks like. So we basically monitor one quasar here. And this is sort of in the new approach that takes the data much more frequently. You have, so the colored points are the measurements in the catalog. Then you have the estimate going as the black lines through here. And you also have, in addition, when the queries, when the science queries need an estimate. And so we can basically monitor here very well if there's any issues and problems with this. And well, this is just showing the time balance. I want to go faster through this now. So here, what we have is the, we had sort of to reprocess some data because of inaccuracies in the flux. And that has been sort of a considerable amount of work, which then has this new scheduling sort of improved. And actually in the few recent months, we have not had any of those. So this is now giving you numbers for the direct estimate of the direct calibration of ALMA data. Here you have you can estimate the antenna efficiencies, and you have the average numbers for nighttime data, but we don't see too strong variations with time or season. And you can see the RMS here, which is of the order of, it's from 2.3 to 5.6%. But this is a limited set of data. There's more variation. And this is the comparison of this direct method with our normal calibration. And you can see that that ties in reasonably within 3% with some additional scatter. So this is just taking the average here and the RMS. So now how do we validate sort of the statistics, the accuracy of this monitoring method? And we take out one measurement and we estimate from the remaining measurements what this measurement should be. And you have to be careful. This is a pretty well-known standard way of doing, but not for time series. So for time series, you have problems that, of course, when you take this out, the cadence changes. You may have different distributions in your queries and in your measurements, etc. And so to overcome these problems, we basically went to simulations. So we have I cannot. There is a paper on using a stochastic model to quantify the behavior, the variability of the quasars that ALMA uses. And we use the same model to make these synthetic light curves and these simulated catalogs. So these are basically at the same time, measurements at the same time using these light curves. And we can, on this catalogs, then assess, and this is also unfortunately not exactly what I wanted to show, but so here we can then compare the statistics on the measurement with actually the statistics on the queries with given the science data, and that does change quite significantly. And there's a sort of a normalization factor in here which shows how conservative our errors are by about 40%, etc. So we can also test various. Yeah, I think I should to the end. Two more things I would like to say quickly, if that's okay. So we also have data where we have solar system objects common in one data set. And that allows us to do two things. We can quantify the relative flux transfer from one data set, and we can get information on the solar system objects and on the absolute calibration. So here's an example of band 7 data, and you can see how they're scattered. But actually, these are outliers that can be removed. You can see some changes with time. So this is Uranus against Neptune, and that changes of the order of 3-4%. You can see here, so the way the outliers are removed, I can demonstrate here. This is the autocorrelation amplitude, and you can see how the color of that changes basically with the dispersion. So you do find a tighter correlation when you remove data that do not have the same quality atmospherically speaking. And so basically the accuracies we are getting here is about 1% in band 3. And depending on conditions, 1.4 to 2.5% in band 7, and then about 6% in band 9. So this is about 650 kilohertz. And the same spectrally. So there our accuracies are 3, so I mean less than 0.5%, even in band 9. And there's offset spectrally between the models, so Neptune and Uranus, that we are discussing with the modelers now. So there's Uranus against Mars does actually show the same effect, and against Neptune not. So I think we can identify which model is causing the problem and see how to improve this. So yes, I think I stop now. Sorry,
Questions for Roger? And yeah, you can speak up.
So, I don't know if it's helpful, but there's a high signal noise measurement of alpha sen in band 7, and you can get a pretty accurate calibration independent of all the planets relative to the sun, the sub-millimeter measurements of the sun. Done it, and it's good to 7% without doing a lot of work.
Okay, yes, that's interesting. I mean, we have been exploring other options. There's a set of asteroids. We have tried for the stars. There was some work done. We have not seen really sort of an advantage because, I mean, the planet models are well studied, and we think we can maybe improve them, and the flux transfer does seem to work.
This has the virtue that it's model independent. We're comparing a real star with a real star.
Right. Okay. Yeah. No. Definitely. Yeah.
So you mentioned resolving out flux with a big array, but even for your individual antennae, do we really know that you're getting all the signal and also not getting stuff in for sidebands? I mean, I'm not a radio astronomer primarily, but the beams are very messy. So it's an interesting question. How well can you get the absolute flux even from a single dish telescope?
Well, we're not having a single dish telescope. Maybe that's the answer, right? I mean, I think the interferometers are much cleaner in that sense because you only get the correlated signal from the source. You do have the atmospheric terms, yes, but in terms of the other problems that you typically have a single dish observing, we do not have that quite the same. So I mean, I think it's probably properly quantified what I showed you, which are the terms that are relevant. I mean, spillover and things like that is not really something that we have to deal with.
So you're confident you're not losing any flux even in your small group of telescopes?
Well, yes. I mean, I mean, the single dish telescopes are not as well calibrated. That's sure. I mean, that's yes. Those are of the order of 5 to 10%. Yeah.
Any other questions? Nothing online? Quiet? Okay, then let's thank Roger and we're going to move on. We're right on time. We're going to move on to the discussion, and just a quick announcement right after the discussion. If you want to be in the workshop picture, then let's exit through this door, and we're going to take a picture on the stairs in front of the building. Just a quick ad.
Yeah, that one.
Yeah. Okay. And Greg is going to lead the discussion.
All right. So if I remember right, we got 3 more discussion sessions. So Friday lunchtime, we're going to do white dwarfs. This afternoon, we will talk about ground to space calibration issues. And Lisa, I'm looking at you. You're supposed to be nodding. Yeah, you got it, Greg. This is good. And then what we're going to talk about now, I've been sort of collecting notes, but I'm hearing the building of a wish list for, well, I think what amounts to additions to CalSpec is one way to describe this, but basically thinking about what kind of standards we want going forward and incorporating those into CalSpec if possible, and thinking about the mechanisms of how we do that. But I thought the most important thing was the wish list. So people should write this down. So far, we've talked about faint white dwarfs. That's already happening. I don't remember how many we had in cycle 3. It was a handful. 5. That's a handful. And we're planning to continue that with cycle 4, right?
But there's already more in CalSpec, right? Hubble also contributes to CalSpec. It's not just JWST.
Not just JWST. Okay, yes. HST has how many of the faint white dwarfs already?
19.
Damn. Okay, good. They're ahead of us. I say us from the JWST side. All right. Faint white dwarfs. K giants for the NEO surveyor.
And traceability to previous missions, which is very important, right?
Right, because we've observed those with IRAC, so that certainly helps. And then now Suzuki had talked about the black body stars. You had, where did it now go? Yes. And you had mentioned you have a cycle 4 GO proposal in, is that right? Good. All right. So I think the idea is that we should be prepared for that to be successful, and then we can figure out how to model those, incorporate those in, right? So that's a short list, and that just deals with a narrow range of people. And kind of the whole point to this workshop is to expand perspectives here. So y'all have to speak up and expand perspective. The only other thing I have is I had a conversation with somebody on NearSpec about duplicating sets. That would be the Spitzer Atlas of stellar spectra. At some point in any spectroscopic mission, we sort of start looking to fill out better space for stars. I wanted to talk to Carl about this because I believe that you have covered a bucket load of parameter space in your extinction searches. They know. That's
OB stars. OB stars only.
Right. That's okay. Just OB stars. So that's another thing to talk about. But I'm not sure if we really want to try, F-type dwarves for calibrators. But anyway, I'm going to stop talking and people can start adding to the list. Or just yell. I don't know.
Oh yeah, that's right. I guess I don't need. Well, I'm not gonna add to the list. I'm gonna put a request to for people to think what targets to add to the list. I'm coming back to the UV, Ralph. So we heard, for example, from Rachel, she highlighted that for the COS mode covering the bluest wavelengths of FUV, G130M 1222, our absolute flux accuracy is 10% because the fluxes in the models there at the bluest wavelengths are very low, and then the models have uncertainties. I know, we just heard about UVEX, so I think if we're pushing to, 1100 angstroms, we definitely can't forget about UV standards. So I don't know if people have thoughts. And we have HWO coming, so that'll be helpful in a couple decades as well.
UV standard, FUV.
Those are white dwarfs, right? FUV, no?
We are using white dwarfs, yeah. But I mean, we're talking about not our HSD primary standards, right? We need something new for the bluer wavelengths, like 1100 angstroms below.
What does one look at? This is so far out of my wavelength.
There's ISM lines
I
that,
don't want to talk about X-rays. Yeah, go ahead.
The ALMA slide is still up there. I think we shouldn't forget about the gap between the mid-infrared, which is as far as JW is going these days. We've got the far infrared, and we need to tie into the radio. We really need to tie the entire electromagnetic spectrum together. We can't do it with one object, obviously, but we need to build a ladder that goes all the way from those X-rays that somebody was mentioning, which are contamination in some people's perspective, UV, visible, infrared, all of the infrareds, and tying it to the radio universe. Cosmology questions, the exoplanet questions, the stellar evolution questions. They have aspects in all of those wavelength ranges.
Any ideas? I mean, you had mentioned, George, you had mentioned Alpha Cen. I remember talking to a colleague of mine who started out in radio saying that they used to calibrate at VLT with IRC plus 10216. I found amusing because it's a Myra. Yeah, Carl.
I mean, maybe for going to longer, to getting longer wavelengths, maybe we could start with the far infrared and Prima and find out what their sensitivities are and what their plans are for flux calibration. Jumping all the way to the radio is hard. Yeah, so we should start bootstrapping our way out. And I would think that there's definitely, given that Prima is in phase A, that might be a more straightforward starting point for expanding the wavelength range, possibly of Cal spec, if they're doing stars. Maybe one of the things to think about is, are we going to expand to other kinds of objects in our, whatever Cal spec means in this expanded thing?
So I had a similar comment. We really have to add planets, not that we have to maintain it all, but just pointers to say, consult the people, say, what's the best Mars model? What's the best Uranus model? And just have a cross-reference, point to it so you know where to find it if you need it. And so if you're going to go to long wavelengths and towards the radio, you're going to need that.
Yeah, I think from a broader perspective of calibrating at all wavelengths, this is great. From a somewhat self-interested perspective, is this Cal spec?
It's a spectral model.
Well,
at some point, CalSpec becomes one of those web pages with lots of links that eventually go stale on us, right? That's probably not.
Well, I'm just, Ralph has a vision for Cal spec, I'm sure.
You're going to take it over.
Yeah, well.
Yes.
So what's your vision for CalSpec?
I'm not sure it includes planets.
Well,
okay.
Not at this juncture. I wonder if we're straying a little beyond what are the needs for Cal spec to what are the needs for flux calibration in astronomy, which I might like to imagine is a larger topic than a more focused Cal spec discussion.
Let me try something. So I think that CalSpec is, I think of CalSpec as a repository for spectra, up until this week, models of spectra, but that's not really correct.
And spectra, no.
Yes, and
Cal
observed
spec is
spectra.
observed spectra and models.
Repository of spectra that have been calibrated to a uniform database, a uniform standard, basically. So they're basically, you can pick randomly from CalSpec and feel comfortable that the star you picked is calibrated to the rest of the parent sample. That to me is the idea. And so at some point you gotta go, no, we don't do planets, but here's some papers. So in terms of, I'm kind of happy to hear that K-Giants could make their way back into this, but I actually like we talked about, probably empirical spectra of said K-Giants.
So that's where, let's just emphasize that point. Cal spec is not models of stars. Cal spec is spectra, which are both models and spectra.
Yes, George.
Yeah, I think there's a bit under the hood in that uniform standard, because going forward, one hopes there will be contributions to CalSpec from a variety of sources, and there has to be some mechanism to evaluate the standard against which some contribution really has been made. So it's not all going to be based on HST STIS measurements. So you got to figure out how to evaluate stuff and then maybe put some kind of comment on things that reflect the standard rather than uniform. I mean, suppose that 30 microns, I can only do 5%. Rule 1, you don't put it in, I don't think so.
So we need to calibrate out into the mid-IR in order to calibrate the standards that would be for Prima, for example, which is another leap, right? So it's about building the ladder. But you're right, I mean, STIS is not going to operate forever. So we can't observe everything with STIS.
It doesn't work very well at 30 microns either.
No, I don't think so. Never used it. Yes.
I guess I'd like to put in more of a request, I guess, which is for sort of spectral diversity across all the wavelengths as well. We want diversity of stars. And the reason I'm saying this is because I'm working on a UV imager mission. My passband is between 1,000 angstrom and about 1,500. And looking through CalSpec and filtering out, so some of the spectrum don't even go down that far, but filtering that out and then filtering out too bright, too dim, or whatever, all I'm left with are just white dwarfs that all pretty much look the exact same. And that's not as useful for me when I'm trying to recover the passing of the period. I can't do much with that.
Would you be interested in the O stars that we're adding to it? Or do you have any other thoughts? Like diversity it's a wide open topic by definition. Do you have any specific examples of what you would want?
Well, I'm interested in picking Lyman alpha. So if there's any stars that are just Lyman alpha piece, and that's it. Great for me, but I don't have any suggestions.
Yeah, I think
stars.
Diversity in the far UV is harder than diversity in the optical. I think the idea of diversity in the types of standards that we have or types of spectra we can use is great. We've heard about it for passband characterization. I guess the challenge is it has to have far UV flux.
Yeah.
And I think that is severely limiting, right? For your particular case, right? We're very limited in the far UV by what actually has emission there. Only hot things.
We're limited to stars.
Can't think of anything else.
Yeah. And of course, I mentioned the stars, but I have it against those.
What?
The O stars. I have it against the O stars. But that's
But I think the idea.
Argue about that over a beer.
Well, you brought up, a diversity of sources. Absolutely, that's what we wanted for JWST. I think we've heard it for other people. We need to get a larger, not just, maybe we shouldn't just be thinking about faint white dwarfs, but faint A dwarfs and G dwarfs and K giants, right? And that would give us a more diversity of spectral shapes, which I have learned in this week is needed a lot for the surveys to deal with passband effects, et cetera. So
someone mentioned earlier K dwarfs. Did I hear that? Nobody knows.
Not here.
Could be my imagination.
Greg.
Yes.
Yeah, one thing that's important, at least for a lot of missions that are planned or flying, is location of calibrators, because it's much more efficient for missions that are, have a big sun shield to point to the ecliptic poles, because they can access that anytime they want to. And unfortunately, there aren't, Ralph didn't go pick sources primarily in the ecliptic poles, probably because it's hard to do, and you pick the ones you know and love and have good data for. So, but that would be useful, because that makes it easy to hit the calibrators, and also for missions to hit the calibrators at the same time if they wanted to do some sort of observation after that, where they wanted to make sure they were really well calibrated relative to each other.
Yeah, I picked 30 K giants and 28 dwarfs for the IRS for Spitzer, right? I couldn't find any A dwarfs remotely close to the continuous viewing zones. But pretty much all the K giants were in one CVZ, or they were near one pole or the other. So for primary standards, we could get
a transfer standard, right?
Yeah, transfer standards. I agree. And we'll talk about, we need to have stars of different colors to sort of push how well people know their filters. Yeah.
I mean, finding targets is one of the challenges. This is something that the ground-based surveys can help with. If we said we wanted A dwarfs or G dwarfs in the ecliptic poles, is that something that is, I don't know, this is a question. Is that something we can dial in?
Well, with Gaia, you can do that. If you trust their mechanism of assigning stellar temperatures and surface gravities at extinction. So if you ask for A stars within the parameters, say 9,400 to 10,300 in surface gravities from, say, 4 to 6, you get 1 million sources back from the Gaia database. I did this a few days ago. And strangely enough, about 4,000 of them are said to have low extinction, which I didn't think existed. 15th magnitude A star with less than 0.2 magnitudes of T extinction. I thought there was no such beast. But I was going to prove to everybody there was no way to go down there, and I found these candidates. I haven't looked too much further, but the possibility is there, and you could do the same for G-type stars or K-type stars. And as long as you trust their machinery for getting the surface gravities, you would be able to select what you want.
So does anyone on one of those surveys want to comment about that?
I mean, there is, I think, Gaia is an obvious source of sources, but there is now a huge number of surveys doing spectroscopy from the ground, really good quality. We have Sloan, now we have DESI, we have EFS, we have WIC, we will have Foremost, and these surveys are doing medium resolution spectroscopy of tens of millions of stars. We can combine Gaia information, spectroscopic information from those surveys, identify very large numbers of good candidates that then can be followed up. One problem we have been discussing the problems with CAD spec and the reference stars we have there, and the fact that they are tied to models and so on. But in spite of all of these issues, the fact that the CAD spec database is so small, I think is something that we can fix. Of course, we cannot probably fix it 5 or 10 years from now, but now is the time, maybe before we lose STIS, to really put an effort, right? Because building the current database took a long, long time. It was very, very hard to find time to schedule the calibrations when there was such high demand. But now maybe we are in a better position to expand, and get very good candidates for calibration from base surveys and Gaia, and follow them up with STIS and tie them to CAD.
So what's the best way for people to get time on HST or JVST? Do we just apply the geo time? Or do we want to like talk about this with some of the cross mission? We have a cross mission calibration group.
Yeah.
We have the JVST, the absolute FLUX Cal group. Should people contact us? Should they submit?
Well, so, okay, so I think that's a good question. One of the questions is how many sources would we want to expand to? And what are the quantitative criteria that would justify X number of sources, right? So it's really important to be very quantitative. I would say that if it's another mission or observatory and it's core to the success, then maybe there is a cross mission at the higher levels that can be discussed, as JWST was helped out by Spitzer and TESS and HST, but not through proposals, through talking with the directors. So at that level, it's possible to do that. I think that has to be pretty core. If it's expanding to larger samples, because it would be great to have, but it's maybe not as critical, then probably geo proposals. Calibration geo proposals is the way to go.
But you need a menu of what observations make sense.
Yes, you need to know why.
You can't just say somebody says I needed a resolution of 100,000 spectrum because it would make a good calibrator. There needs to be a lot of work and figure out what you need as a function of what kind of calibrator.
And what are we going to get out of it science-wise?
Yeah.
So I'm comfortable saying you should email Carl.
I'm willing to provide a clearinghouse.
Copy me so that.
But think about, I think we should also think about it more broadly than just STIS, right? We also now have JWST, so we can actually think about spectra from the far UV to the mid-infrared, which we think are going to be well calibrated. We're still working on the JWST, but having JWST calibrated spectra that are very similar to STIS looks like what's true, what's going to happen. So we're not limited just by the STIS wavelengths.
Well, but there are other things, like you don't want to pick stars that are rapid rotators.
Oh, right. Variability. We need to know all about variability, rotation.
And large ground-based telescopes can provide much better spectra than you can get from anything in space that do that issue.
All about
high
planning it.
spectral resolution.
In order
100,000 isn't good enough for you, George?
What's 100,000 in space?
STIS. Does 100,000 resolution spectrum. Yeah. I just wanted to make sure you didn't denigrate that.
The problem with STIS is it runs out of signal.
Fair enough. So if you want to say that, sure.
Yeah, well, you need high spectral resolution on a faint object at decent signal to noise, and there isn't anything in space that does.
So I think the idea is it's important to plan ahead so that we can vet these lists early in the game, and that requires ancillary data from other telescopes. And then we can go to JWST or HST, with a list that's been pretty well curated at that point.
Yeah.
But I'm trying to make the point, you want to go to maybe Gemini also. I mean, you don't want to just think, well, I've got HST, we're going to solve the whole problem with HST.
Or not correct. Cross observatory is the way to think about this.
And that means you have to get the directors or whoever influences the schedule on board. There has to be an agreement across the necessary facilities that they will all participate.
Someone had mentioned like a CAL proposal. I think the CAL proposals are designed to be, like, if you do a cal proposal for MIRI, the idea is that you're somehow going to improve calibration in
The
MIRI.
instrument.
So I think it would be a GO proposal slash a DD request, slash, we would do it through the cycle 4 calibration program or cycle 5.
There are mechanisms to do this, I think, with all observatories.
Yes.
That's not the complicated part, at least from my experience.
Complicated part is to get them used on a consistent set of targets.
I think CalSpec probably also needs especially in talking about expanding it and being selective of source types, it probably also needs a better interface and more information attached to the targets and the ability to select CalSpec targets based on bands of interest, spectral types of interest. Is this a rotating star or not? Where are this?
Yeah, I agree. We need to expand the metadata.
Interface is also something that can show up as an archival proposal to create the interface and have the website be more than a selection of tables.
Yep.
That's what we are thinking.
Yeah, so we're already going that route. We're thinking about that, of how to do that.
Talk with me?
Okay, I have many people to talk to. Excellent.
Susanna, did you want to say something?
Yeah, from my perspective, I think what's important is deciding how many stars, which stars we're interested in obtaining data for. And I think the other conversations are important, but I thought we were talking about what star, what does, I think Carl said it. What does the community need? I would like to focus on that. Some of the other discussions are great. I'm sure that they're as important as what does the community need and how do we get that? That's my 2 cents. Inflation.
Just focus.
Nothing.
All right. So we can continue this conversation with the meeting, and also you can talk to Carl and Annalisa because she is also on these groups. And anybody else you can drag in, and we have email. And I think it might be time for a picture.
Yeah.
You want to herd us out that door?
Don't run away.
Yeah, no,
Not